Hello students, have you ever played a treasure hunt game with a map where you had to go 5 steps north and 3 steps east? Now imagine your friend lives 36 kilometers east and 15 kilometers north of your home. The question is, what's the shortest route? Do we run 15 kilometers north, then 36 kilometers east, or do we just cut across in a straight line? Well, of course, we'd want the shortcut. And mathematics gives us exactly that through the Pythagoras theorem. The distance equals square root of 36 square plus 15 square, which comes out to 39 kilometers. See? Coordinate geometry is like Google Maps, but powered by math. Alright, let's warm up with something even simpler. If both points lie on the x-axis, say A at 4, 0 and B at 6, 0, then the distance is just 6 minus 4, which is 2 units. That's like counting steps along a straight corridor. Now, if both points are on the y-axis, say C at 0, 3 and D at 0, 8, the distance is just 8 minus 3, 5 units. So along the axis, we don't need fancy formulas, just subtraction. Easy peasy. But life isn't always that simple. Most points are off the axis, and that's when the real fun begins. Now let's tackle the general case. Suppose we have 2 points, P with coordinates x1, y1 and Q with coordinates x2, y2. If you join them directly, you get a diagonal line. But diagonals are tricky to measure directly, so we use a trick: construct a right-angled triangle. Draw a vertical and a horizontal line to make a neat triangle. The base is the difference in x-coordinates, that's x2 minus x1. The height is the difference in y-coordinates, that's y2 minus y1. Now, apply our old friend Pythagoras. Distance PQ equals square root of open bracket x2 minus x1 whole square plus y2 minus y1 whole square close. And voila! We've arrived at the magical distance formula. Let's test this formula in a special scenario. Imagine a point P at x, y and the origin O at 0, 0. The distance OP equals square root of x square plus y square. Simple, isn't it? Also, note this: whether we say distance from P to Q or from Q to P, the formula doesn't change. It's like saying the distance from Delhi to Agra is the same as from Agra to Delhi. And here's another cool property: distances always follow the triangle inequality. The sum of two sides of a triangle is greater than or equal to the third side. That's why in real life, shortcuts never end up longer than the long way around. Let's take an example. We have 3 points, P at 3, 2, Q at minus 2, minus 3, and R at 2, 3. Do they form a triangle? Let's calculate. PQ equals square root of 50, about 7.07. QR equals square root of 52, around 7.21. PR equals square root of 2, which is 1.41. Since each pair of sides adds up to more than the third side, yes, they form a triangle. But hold on, PQ square plus PR square equals QR square. That means angle at P is 90 degrees. So this isn't just any triangle, it's a right triangle. That's like discovering your boring triangle has been hiding a right angle all along. Let's crank it up a notch. Consider 4 points, A at 1, 7, B at 4, 2, C at minus 1, minus 1, and D at minus 4, 4. Do these points form a square? Step 1. Calculate all sides. Ab BC, CD, and DA each comes out as square root of 34. All equal, good sign. Step 2. Calculate diagonals. AC and BD both equal to square root of 68. Perfect match. So, with all sides equal and diagonals equal, this quadrilateral is a square. Isn't it satisfying when the math works out so neatly? It's like fitting puzzle pieces perfectly together. Here's a relatable classroom example. Ashima sits at desk A with coordinates 3, 1. Bharti is at desk B with 6, 4. Kamila is at desk C with 8, 6. The question is, are they sitting in a straight line? Compute distances. Up equals 3 root 2. BC equals to root 2. AC equals 5 root 2. And look, up plus BC equals AC exactly. That means the three girls are collinear, sitting perfectly in one line. So next time someone argues about seating arrangements, just pull out the distance formula. Let's tie everything together. We discovered the distance formula. PQ equals square root of open bracket x2 minus x1 close square plus open bracket y2 minus y1 close square. We applied it to special cases like points on axis and distance from the origin. Then we used it to check whether points form a triangle, to prove a quadrilateral is a square, and even to test collinearity. This formula is a bridge connecting algebra and geometry, turning coordinates into shapes and shapes into proofs. And that's the magic of coordinate geometry. It makes the invisible connections visible. In the next video, we will explore the section formula, which tells us how to find the coordinates of a point dividing a line segment in a given ratio. It's like finding the exact middle seat in a row of friends. See you there.